So, welcome to the last lecture of the conference. There's still a panel to go, but this is the last speaker, and we're delighted to have Massimo Bianchi, who's going to talk about multipolar structures, photon spheres, and quasi-normal modes in fuzzballs. Thanks indeed, and take it from here, Massimo.
First of all, let me thank the organizers. It's been a very nice web conference. I enjoyed all the talks, and I will try to make a nice talk for you. So this is based on work done in collaboration with Dario Consoli, Alfredo Grillo, Francisco Morales, and also more recently with Paolo Pani and Guillermo Raposo. And I will also talk about a little bit of the work with Andrea Dazzi, Alice Aldi, Maurizio Firrotta, and Antonio Marciano. There is also ongoing work with Taishi Ikeda, Claudio Argento, Giorgio Di Russo, together with other people in the collaboration, and an earlier work with Lorenzo Pieri and Natalia Zinato that we will use a lot. Sorry. How do I change slide?
Are you sharing full screen? Are you using Zoom or?
No, it's preview. But click on preview application.
I'm sorry.
Just click on the preview. Okay, now you're good. Now just forward. I think you're good. You've got control.
Okay, very good. So after a very short preamble, this is kind of a follow-up to Francisco's talk at the conference in June. I will talk a little bit about the critical geodesics, photon spheres, and the Lyapunov exponents. I will then describe the computation of mass and spin multiple moments for some special microstates, the three center microstates. I will talk a little bit about quasi-normal modes. This is mostly work in progress, and I also will give a preliminary discussion. I will then change gear, if you want, and I will talk about swing correction to the gravitational or electromagnetic memory effect. Then I will give a summary and an outlook. Sorry, why should I?
Somehow that means that the frontmost application is not preview. You need to bring preview to the front. So click on preview and bring it to the front.
You open the file, open with preview. What Nick is saying, just close the file and open it. Instead of open with Acrobat.
Yeah.
Sorry, let me. What?
The other option is to share the full screen. And take the preview to full screen, and then once it's full screen, everything is much better.
Hit escape and see what happens.
I don't understand. Sorry, let me.
Okay, you seem to be doing it now.
Okay. No, sorry.
That's good. Oh, you're an Acrobat reader. That's possibly part of the problem. Okay.
Okay.
So share the full screen.
Wait. Let's get the thing open in preview. That's an Acrobat, so I don't know quite what will happen.
Close the file and say open with preview.
Yeah.
Close the PDF.
Close the PDF.
Yeah.
Close again to the file.
Which file?
Whatever file your thing is in.
It's a PDF. So
yes, just find it.
Instead of double click, you just go with the. No, don't click.
That'll open it. That'll open it. And where is the file?
Somewhere here.
Yes, open there. Now the right button. The right button.
Where's the file? Okay.
This is the file.
Go to file. To hit info. Okay.
Oh, the right button.
Right button.
Yeah.
The mouse right button.
No. You opened it. Okay.
Tap with two fingers.
Close it again. Close it again.
2 fingers.
Now. Hit Command I. Command I. Highlight the thing. Highlight the file. Now, Command I. Okay. Where it says Adobe Acrobat Reader, see down there, halfway down the screen there? Go there. Now, click on that and change it to preview. Right, let go.
Yes. Okay, change
now open it. Just go back to the Finder and open it. No, just double click on the file. You've got it, move the mouse to the right, 5 inches.
To the right.
Move the mouse to the right.
Yeah,
there. Now double click on it. Right, I think. Yes, excellent. View full screen and off you go. No, keep going. Left.
Under view.
At the bottom.
Damn.
Very bottom. Perfect. Now we should be good. See if you can do it now.
Okay. Yeah, it goes.
Good, excellent.
So, first of all, I'm sorry for this. I'm
no
really
problem.
Okay. So these are the two pictures that David Turton has shown, and I was very jealous when he did it. But okay, anyway, the first one is the merger of two black holes and the signal that one can detect. And the second one is a photon sphere of the black hole that was observed by this Event Horizon telescope. So, probing fuzzballs and microstructure, one can do this by scattering massless probes. And as we all know, for large impact parameters, there are small deflections, which are governed, for instance, by the famous and celebrated Einstein formula. For critical impact parameters, the particle gets trapped in an unstable circular orbit, sometimes called that form what is called the photon sphere or light rings. And below critically, there is a big difference between black holes, which are a robust prediction of generativity, very much as an instability of atoms is a robust prediction of Maxwell equations, or get trapped for a long time. Another strange effect appear in fuzzball or other exotic compound objects with microstructure. To show what happens in black holes when the impact parameter is large, the particle gets deflected. When the impact parameter is equal to the critical value, the particle gets eventually trapped asymptotically into the photon sphere. When the impact parameter is small, it gets absorbed into the black hole, captured into the. When you have a fuzzball, this is the case of a two-charge fuzzball in 5 dimension, in the two different planes, you can have either deflection or you can reach the photon sphere, the critical geodesic, or you get scattered back even when the impact parameter is smaller than the critical value. And if you are in the different plane where there is the angular momentum is actually line, you can have a strange effect like kind of a deflection back if the parameter is running in the opposite direction with respect to the angular momentum of the fuzzball. The critical geodesics are the ones that form the photon sphere or the light ring, and near the critical geodesics there are exponentially large deviation for nearby trajectories. These are governed by a law of this kind. RC is the critical radius, and the parameter lambda that governs the exponential growth of perturbation around this critical geodesics is the Lyapunov exponent. Together with Alfredo and Francisco, we set a bound which is related to the minimal impact parameter before the capture by a formula which is valid in generic D dimension and is given by this formula. And when one compares this bound with the bound on Chaos set by Maldacena, Schenker, and Stanford, one finds that this lambda b is always smaller than lambda t, but there is a violation of the bound near extremality, where eventually lambda t, since the temperature of the black hole goes to zero. So while lambda is always smaller than this lambda b that we found, it's not always smaller than lambda t. The lambda plays a very important role in the ring down phase of black hole mergers, because the imaginary part of the quasi-normal modes frequency is precisely proportional to the Lyapunov exponent, at least in a semi-classical approximation. And we will find it again later on, is called the overtone number. For fuzzball, we expect this lambda to be smaller than for the corresponding black hole, and so we expect a longer time scale for the decay of the perturbations. and also because of the fact that the particle can wind around the fastball more than once, there will be echoes in the signal. Recently, with Dario Consoli, Alfredo, and Francisco, we analyzed the problem in 5-dimensional geometries. 5-dimensional black holes are an arena for the more involved 4-dimensional case, as Strominger Vafa told us. And there is a large class of solution of Einstein-Maxwell chain-sided theory that have been studied by Chung, Chwedyk, Liu, and Pope long ago. And this solution are parameterized by the mass, one single charge, and two angular momenta, L1 and L2. The singularity in the geometry appears at a new coordinate called rho usually, rho square equal to 0, which is related to the standard radial coordinate r by this relation, r squared plus L1 squared cos theta squared plus L2 squared sin theta squared. Typically, they have an ergosphere where the time-time component of the metric vanishes, and the horizon are determined by the value of r squared plus minus given by the mass and the angular momentum and this combination. The extremal case, which corresponds to the case when two horizons coincide with each other, correspond to 0 temperature, and this is achieved when the charge is equal to plus or minus the mass. Clearly, the charge can be positive or negative, minus plus 1/2 the difference or the sum of the two angular momentum square. In the extremal supersymmetric case, like the BMPV black hole after Breckenridge, Myers, Pitt, and Vafa, the charge is equal to plus or minus m, and the two angular momenta are equal or opposite to each other. These geometries can be uplifted to 6th dimension, to the case in which the three charges Q1, Q5, and QP are identical. And there is a capping which is possible when the angular momenta L1 and L2 satisfy a relation of this kind. That is L1, L2 modulus minus L1 square minus L2 square is equal to R plus square less than 0. The capping is possible when R, the radius of the circle that uplift the geometry to 6th dimension, and the two angular momenta R determines in terms of two integer numbers called m and n, and the supersymmetric case that was studied by Giusto, Matur, and Saxena is achieved when m is equal to n plus or minus 1. One can study critical geodesics in this geometry and determine a Plejano exponent. The geometries have several conserved quantities, E, J1 and J2, or J phi and J psi. And there is a separation constant, K, similar to the Carter constant for Kerr black holes in 4 dimension, which relates the angular part of the Hamiltonian. Theta is the latitude, and r is the radial direction. So this constant is fixed, and it's positive because it's the sum of squares in the angular part, and it's identified with a combination of PR square with a minus sign, a certain function delta r that appears in a metric, plus terms which are not very illuminating to show. Now, one can study, as we did before, the evolution of the radial variable with respect to the time coordinate, which is governed by the derivative of the Hamiltonian with respect to the radial momentum. I'm sorry, there is a mistake here. This is NE. This is the energy, sorry. Which can be parameterized in terms of a function only of the radial variable that we call calligraphic R, and a function of both the radial and the angular variable theta in the denominator, which appear from the derivatives of the Hamiltonian with respect to the energy, which, as you can see, appears also in the angular part. Now, to simplify the analysis, one can choose to work in theta equals 0 hyperplane, and when theta is equal to 0, clearly one has to set j phi equal to 0, and the analysis simplifies. And the critical geodesics correspond to taking r of r equal to 0 and r prime equal to 0. So this determines this parameter rc, which is the critical radius. And in terms of the critical radius, one can express the Lyapunov exponent as this ratio of the second derivative of r computed at the critical radius and the value of this function s of r and theta computed at the critical radius, and there is this knot to denote that we chose to work at theta equal 0. So for geometries free of naked singularity, we check that the Lyapunov exponent is always smaller than the Lyapunov exponent for the Schwarzschild-Tangerlini black hole, which is the generalization of Schwarzschild black hole in higher dimension with the same mass. And the explicit results that we got for various cases are shown in this picture, in this slide. You see that for the Schwarzschild-Tangerlini black hole, you saturate the bound d minus 3 divided by 2 times the minimal impact parameter. For Rising Northern black hole, you don't saturate the bound. The Lyapunov exponent is always strictly smaller than this value. For Myers-Perry black hole, which are black holes which are neutral but with arbitrary angular momenta L1 and L2, you get an expression which is a little bit more evolved, but you can check that is always smaller than the bound that we set before. And this is the same for the case of the Breckenridge-Myers Pitten-Vafa black hole, which is an extremal black hole with charge equal to the mass and the two angular momenta which are opposite to one another. In terms of a new variable psi, which is rho square, and in this case is simply equal to r squared plus L squared, because L1 is equal to L2. So this relation between rho and r is simplified, because cos squared plus sine squared is equal to 1. The critical impact parameter in theta equals 0 plane is given by this expression, and the Lyapunov exponent can be expressed in terms of the critical radial variable psi by a relation of this kind. And once again, one can check that this is smaller than the bound. In the general case in which none of these conditions are satisfied, that is, you take Q, M, and L1 and L2 to be arbitrary, only numerical analysis is possible, and we check that in the small L2 region where the solution is compatible with the black hole asymptotics, both lambda plus and lambda minus are strictly smaller than the case of the Schwarzschild-Tangerlini black hole. For not so naked singularity, that means singularities that are covered in a sense by the photon sphere that appear for large positive L2. One of the two Lyapunov exponent is smaller than the bound, and the other one exceeds the bound. And for over-rotating larger negative L2 solution, only L out is defined, and it's smaller than the Schwarzschild-Tangerlini Lyapunov exponent. For J-Mart, we check that generically for N and M arbitrary, the Lyapunov exponent is smaller than the limit when these two integer numbers go to infinity, which is smaller than the bound set by the Schwarzschild-Tangerlini black hole. The plot for the Lyapunov exponent for J-Mart and for GMS is given in this picture, and the Schwarzschild case is up here. Actually, this is Schwarzschild-Tangerlini. It's up here. And the SUSY case that corresponds to GMS geometries is represented by this case here. And the case with n plus 10 or n plus 100 are shown here. and the limit L infinity is shown here. And you can see the bound is always satisfied. Now let's change the subject and go to the multipolar structure of fastballs. As we know, in general relativity in 4 dimensions, there is a no-hair theorem that tells us the most general geometry compatible with black hole asymptotics is the Kerr-Newman black hole that has angular momentum expressed in terms of the mass by this simple formula. It's proportional to the mass times a parameter which we usually call A. And the multipolar structure is very, very simple and peculiar. The mass multiples ml plus I times the spin multiple, we will define them more precisely later on, are proportional to the mass times this parameter A multiplied by I to the power L. And even though we usually think of astrophysical black holes as black holes which are neutral, because typically plasma discharge effect tend to disfavor charged black holes, in a scenario in which you have dark photons and nearly charged dark matter, or holographic or string dark photons, it is possible to have black holes which are charged with respect to these dark photons. And so you can also consider the possibility of having Kerr-Newman black holes. Typically, the structure of the multiple moments for Kerr-Newman black hole is identical to the structure of black holes, because the contribution of the stress tensor of the electromagnetic fields is subdominant at large distances. The possibility of exotic compact objects or fastball is not excluded by a gravitational wave observation. Especially, there are 2 events, GW 1908-14 and 1905-21, where one of the 2 components of the binary system either is too light, in the case of 1908-14, or too heavy, at least one of the 2 in the case 1905-21. So there is room for exotic compact objects or non-trivial microstate geometries in these cases. The general method for extracting multiple moments from arbitrary stationary space-time was devised by Geroch and Hansen and by Thorne, and we will generalize these to microstate geometries. In the case of generic microstate geometries, one has no axial symmetry, no equatorial symmetry, so the multipolar structure of this geometry is typically more rich or richer than the case of Kerr black holes. Typically, in events which are related to the gravitational wave observation, one can hope to measure, for instance, the second multiple moment of the mass distribution, or the third multiple moment of the spin distribution, and then put constraints on the fastball or other exotic compact objects. This will be more, the bounds will improve with space mission like LISA or alike. Or the advantage of studying the multiple moments is that they are easy to extract from the asymptotic of the microstate geometries, which are regular even in 4 dimensions. Extracting instead quasi-normal mode frequencies harder because, for instance, the geometries are not completely regular in 4 dimensions, and then they need an uplift to 5 dimensions. The only caveat is that in order to extract the multiple moments, one has to work in asymptotically Cartesian mass center coordinates, but as we will see later on, this is the case for the microstate geometries that we will study. As I said already, the multipolar structure of fastball is much richer than Kerr or Newman. And the strategy to extract a multiple moment is to construct the Killing-one form, which is always present for easy to define for stationary space-time. Then define the multiple moments, identify, for instance, dimension and ratios, which we will compare eventually to Kerr or K-Newman, and use some specific multi-center geometries like the three-center solution that we studied some time ago with Lorenzo Pieri and Natale Zinnato. And then we will perform a statistical analysis based on a uniform distribution, which definitely is not realistic, and we will comment on this later on. The mass multiple moments are defined in terms of the harmonic expansion of the external derivative of the Killing form, and performing the star in 3 dimensions, and then taking the integral over a sphere at large radius. Similarly, one can define the spin multiple moments starting from the decay. The mass of the space-time is defined in terms of the M00, L equals 0, M equals 0, and the spin is defined in terms of S1M. In particular, the invariant information on the spin is given by the square root of the sum of the square of S10, S11, and S-1. One usually defines the ratio between the spin and the square of the mass, and call it chi. It will appear later on, so I'll define it here. And one can define dimension and ratio, not of M over S, but of M and S with respect to the mass to the power L plus 1, in this way, or different dimensional ratio which are related to the previous one by taking, sorry, there is no hat here, sorry, there is a misprint here, by dividing by this dimension object chi. Also, one can form quadratic invariants. Sorry.
May I ask something?
Yes, sure, please.
Your MLM, do they give the same thing as the Bondi mass aspect, or is it something different?
This is different from the Bondi mass.
I see the definition is different, but the result would be different also for a stationary solution?
The definition is different. I didn't check the relation with but the definition is different.
Yeah, thanks.
So I expect them to be different, at least for cases where you have geometries which are not, probably for black holes, they coincide. Now, for Klein black hole, as I said before, one has to go to AC/MC coordinates, and one has to be careful because, for instance, Boyer-Lindquist coordinates, which are the coordinates one usually writes down the metric, are not, they do not satisfy this the condition for being asymptotically Cartesian. If you go to these coordinates that I call r and theta, and I denoted by r hat and theta hat Boyer-Lindquist coordinates, all the information on the multiple moments of the Kerr black hole can be encoded into a harmonic function, h Kerr, which is a sum over all L from 0 to infinity of ml plus I SL times the Legendre polynomial of cosinus theta divided by RL to the R to the L plus 1. And this is the ratio of the mass by this function, which is a complex function. For BPS microstate geometries, this can be constructed using STU n equal to supergravity. This is 4-dimensional gravity coupled to 3 complex scalars and 4 dark photons, if you want. The metric can be written in terms of a function that we call U, and a one form omega dx in this form. This is parameterized in terms of 8 harmonic function that we call VLI, where I runs from 1 to 3, and M, capital M, and KI, also this I runs from 1 to 3. I'm sorry, because I'm denoting this harmonic function M pretty much as the mass. There will be a little conflict later on, but I hope you will not be confused. The value of e to the minus 4u is equal to the quartic invariant computed with the harmonic function replacing the charges of the putative black hole. And the relation between the harmonic function and the 1,4 omega dx is given by this relation. So the star, the three-dimensional star of the omega is given by this combination. For n-center harmonic function, all these functions will be given by a constant h plus a sum of poles with charges which are taken to satisfy the BPS bound. The smooth uplift to 5 dimension requires that the charge and the position of the poles satisfy the bubble equation, and also there will be more condition for the absence of horizon and closed dynamic curves that require that e to the minus 4u is positive, and this combination satisfy this relation. So V times Lk must be larger than 1/2 the combination of the case. For general n, you can expand e to the minus 4u in terms of 1 plus a sum of poles plus a lot of multiple moments. And similarly, you can do for omega. But as I said before, it's easy to extract the multiple moments because they are only determined by this dominant term in the expansion of e to the minus 4u, and by this term in the expansion of star 3d omega. So computing these parameters mu a and ja, one can compute and combine, if you want, the multiple moments into this combination MLM implies I as LM, which is given by this expression. And this combination R A LM is simply given by the spherical harmonic computed in terms of theta and phi, and the absolute value of the position of the center to the power L. XA are the centers, and you take them to the power L. Now, if you focus on n equal to 3 and put, for simplicity, the constant that appears in the expansion of the function V and L, which I called generically here H, and we called, sorry, here V naught and L naught I equal to 1. And instead, you put the constant in M, the capital function capital M, and the function capital Chi equal to 0. And you also take all the charges that appear in the function capital V to be equal to 1. So Q corresponding to the poles in function V equal to 1. Then the equation, the bubble equation, simplify a lot and can be solved by parameterizing, if you want, the charges that appear in the expansion of the function K's in terms of 4 parameters that we call kappa 1, kappa 2, kappa 3, and kappa 4, and a length scale. We will later on also introduce a parameter lambda to rescale these integer parameters kappa 1, kappa 2, kappa 3, kappa 4, as we will see in a moment. Now, as I said, by parameterizing these charges in terms of this parameter kappa, one can find the function V, Li, M, and Ki. And in particular, compute the charges P naught, which is equal to 3, because there are 3 poles in V, and so this sum is the 3 charges that appear in V. Q1, Q2, and Q3 are the charges that appear in L, and are given by this expression in terms of the kappas, Q1, Q2, and Q3. The condition for this solution to BPS imposes some bounds on kappas. In particular, kappa 1, kappa 4 must be positive, kappa 3 must be larger than kappa 2, which is also positive or 0. And the mass of the solution is given by the sum of the parameters that we called mu A previously, and it's given by the combination of these charge P0 and the charges Q1, Q2, and Q3, up to a factor of 1/4, which depends on our normalization. And the angular momentum resolution is a combination of the position of the centers that I call XA times the parameters that appear in the expansion of the one form omega, or more precisely the star of the one form omega. And one can rotate the solution so that the angular momentum is aligned along the z direction. So it's simply given by J times the unit vector along the z direction. The bubble equation, as I said before, imposes constraints also on the position of the center, in particular by parameterizing the distance between the centers 2 and 3 in terms of a parameter we call L. The distance between the centers 1 and 2 is proportional to L times an object that we call square root of sigma. And similarly, the distance between 1 and 3 is once again proportional to L times another combination rho. Now the combination rho and sigma are given by these expressions, which are not easy to remember. And the parameters that appear in this combination are given in terms of the parameters kappa that appear in the parameterization of sorted charges by this expression here, and also here and here. Once again, in order for the position of the centers to be real, one has to impose conditions on this combination A tilde 1, 2, and 3. And the precise conditions are that A tilde 1 is larger than 0 and smaller than 1, A tilde 2 is larger than 0 and smaller than 1, and A tilde 3 is in between 1/2 and -1/2. In particular, this nice fake square that appear, that has to be larger than 0. These are the condition that allow for this fake square to be larger than 0. This appears in the solution for the position of the centers. One can distinguish 2 main classes of solution. The one with kappa 1 equal to 1, so that you see immediately A tilde 1 is equal to 0, rho 1 is equal to 1, and R1, 3 and R2, 3 are equal to L, and L is arbitrary. So there is no bound on the scale of this microstate geometry. While for K1, different from 1, the parameter L that set the distance scale in these geometries is bound above by a value that we call L maximum, which is given by this expression in terms of this A1 tilde, 2 tilde, and 3 tilde. Now, playing with this parameter that we call lambda, one can choose the kappas to scale with lambda or not scale with lambda. For instance, one can take the scaling solution, which has 0 angular momentum and correspond to kappa 1 equal to 1. The mass is given by this expression. And in this case, the triangle is an equilateral triangle with the side which is completely arbitrary, ranging from 0 to infinity. The multiple moments reflect the symmetry of the configuration, which is D3, or if you want, S3. And in particular, the lowest non-trivial multiple moments are m tilde to 0. M tilde are a-dimensional multiple moments. Remember that for us, G Newton is equal to 1/8 pi, and so essentially these multiple moment tilde are a-dimensional, and so these are simply the ratio between L squared and M squared divided by 4. M2 tilde 2 are given by this expression. The expression for this M component equal to minus M are simply given by the star of the LM to the power multiplied by -1 to the M. And also these are the expression form N31, MT3. For non-scaling solution, the situation is a little different. For instance, one can take a solution in which still K1 is equal to 0, but K3 and K4 do not satisfy the scaling condition, so J is even different from 0. And the solution corresponds to an isosceles triangle. And the multiple moments are given by expression of this form, which scale with this parameter lambda. And also one can consider more complicated non-scaling solution by letting not only K4 scale with lambda, but also K3 scale with lambda, so that the mass, for instance, scale with large lambda like lambda square, and also the angular momentum scales with lambda in a non-trivial way. In this case, is the maximum value of the length scale is determined by lambda by an expression of this form in this case, and one can distinguish two different regimes for large lambda. A regime in which L is over the 1, which is much smaller than lambda. And in this case, chi is very small because it's equal to L over lambda cube. The a-dimensional multiple moments scale with lambda square in this way. And the regime where L instead is equal to lambda square, so we are close to the upper bound on this parameter lambda, and one gets scaling of this form for instance, the lowest multiple moments M2 and S3. And similarly, the story for the solution of class D, in which one has 3 parameters kappa that scale with lambda, and one is kept order 1, like kappa 1, but kappa 1 is not taken to be 1, otherwise the scale L is unbounded. And similar for the E-type solution, in which all the 4 parameter kappa scale with lambda. In all these cases, the angular momentum is different from 0, and the expression for generic values of lambda and L is not particularly illuminating. We then perform a statistical analysis of the result. The parameter space, even for this simple 3-center solution, is quite rich, and we only perform a partial exploration. The conclusion that one can draw is that for certain solution, for instance, the ones with kappa 2 equal to 0, the multiple moments are typically larger than the case of the Kerr black hole, with the same mass and angular momentum, bar a few exceptions. In the general case, when all the kappas are different from 0, the multiple moments are typically larger than the case of Kerr for L larger than some critical value, while for L less than this critical value, multiple moments can be smaller than Kerr. Sorry, here is a typo. This is smaller. Now,
question.
Yes.
Say larger or smaller than Kerr. Do you mean which dimensionless ratio are you looking at? You're dividing by the map.
Yeah, let me show you the dimension. We consider dimensional ratio that I called. Sorry. in this these ones which are the ratios of MNS divided by chi to the power L, or the quadratic invariance, which I here denoted by M hat and S hat of L, and are defined by this expression. So,
Massimo, why do you compare to Kerr and not to the corresponding supersymmetric black hole?
Yeah, in the supersymmetric black hole case, only the mass is different from zero. It's not very. That would be all larger than those of the black hole, because the black hole correspond, if you want, to the case L equal to 0. So in the case L equal to 0, one gets back the
right.
charge non-rotating black hole, and all the multiple moments go to 0, or attain a finite non-zero value in some cases. So yeah, okay, I agree with you. I mean, these are supposed to be fastballs of or microstates of non-rotating black holes. So what we are trying to argue here is that even if we expect the distribution of these microstates to be peaked, if you want, at L equal to 0, which is the black hole limit, there will be some deviation from the distribution, which is completely a delta function distribution at L equal to 0, that can affect the behavior of these fastballs with respect to the non-rotating black hole case. This is our intuition or proposal, if you want. Let me draw partial conclusion on this part. In roughly 90% of the cases, the a-dimension or dimensionless ratio M2 is larger than the Kerr cases, which is equal to 1. Even more so for S hat 3. And remember that in the Kerr case, S2 is equal to 0, while in this case, so for the Kerr case, the horizontal line would correspond to this dimensional ratio, while typically we find some result which is different from 0. Independent of the value of Kmax, which we took to be something like 1000, the normalized invariant tend to be larger than, L critical and L max grow linearly with the largest value of kappa. The normalized invariant are always larger than M0, as we argued before, though the individual components may not. For instance, you will see that there are some components which are smaller than the value of, but the invariants are. The non-rotating black hole limit is okay, even when the value L equal to 0 is ill-defined. The growing with the size L, capital L, is similar to what one gets for other objects that have a microstructure different from a fastball like gravastar or exotic compact objects. Yet, for L maximum smaller than the horizon scale, typically chi is much smaller than 1, and this is a difference with respect to equals. Like the Lyapunov exponent that we studied before, which is extremized in a sense in the black hole limit, we see that these invariant ratios are extremized in a black hole limit. Clearly, the method can be applied also for non-BPS fastballs, insofar as the microstate geometry are written explicitly. So it's pretty easy to compute these multiple moments starting from the knowledge of the geometry, in particular these functions that in the BPS case are given by a combination of harmonic function. In the general case, we don't know much about. So if there are no...
Massimo, you're about at the time limit, so can you wrap up in about 5 minutes?
Okay, so let me be very fast on quasi-normal modes. As you know, the quasi-normal modes of black holes can be determined by studying the perturbation around the black holes and bringing radial equation to Schrödinger form. This is possible both in the case of Schwarzschild and Kerr-Newman. The difference between Schwarzschild and Kerr-Newman is that the separation constant in the case of Schwarzschild is known. In the case of Kerr-Newman should be also, it's not known exactly. So one can solve this Schrödinger equation and compute the quasi-normal modes by WKB methods. Now, in the case of fastball, in the two charge case, the analysis is doable. For non-supersymmetric geometry, we know that there is an ergo region instability, as argued by Cardoso, Myers, Matur, Diaz, and Oviedo. In the case of BPS geometries, no such ergo region instability seems to take place, but the analysis can be only performed in a near decoupling limit. For multi-center microstates, the generic case, there is only the time like killing vector. So typically the analysis must be performed numerically. In the axisymmetric case, the equations are not separable, but still some progress can be made by, for instance, going to specific values of theta. The situation seems to be tractable for the equatorial plane in the case in which one has equatorial symmetries. We are working on that, and let me finish with a few comments on this string correction to the gravitational memory effect. As we know, in the case of general relativity or quantum gravity based on general relativity, at least at 3 level, one expects that the soft behavior of gravitons gives, which is coded in the fact that amplitudes with one soft graviton expose a soft graviton pole in the limit of omega going to 0, the frequency going to 0. This is coded in a memory effect, a deformation of the geometry at large distances and late retarded time, which is given by an expression of this kind. As you can see, there is no time dependence on this expression. Only notice this large R behavior. In string theory, in addition to the pole at omega equal to 0, which is here due to the fact that kappa is proportional to omega, there is an infinite number of poles which are on the real axis. So if one performs the analysis, in particular, one can study a very simple toy model in which one studied two let me call them small black holes. There are 1/2 BPS states, for instance, in heterotic strings, and merge them into a non-BPS object plus gravitational radiation. The amplitude using standard Bethe operators for 1/2 BPS object in a heterotic string can be computed exactly at 3 level. and the exact amplitude is as an expression which is very similar to the one that you would get in general relativity. The only correction is this Shapiro-Virasoro factor that contains these gamma functions. And then one can reconstruct the gravitational wave profile at large distances by performing a Fourier transform in omega of this expression. And the presence of the infinite number of poles, which are coded in this gamma function, gives rise to a correction to the gravitational wave profile. So in particular, at large distances, one gets a string correction, which is of this form, which is a series in a variable zeta, which is an exponential of the later retarded time divided by a time scale alpha prime times k hat times p. K hat is the graviton momentum stripped off the frequency. The effect cannot be seen in a standard low energy expansion of the amplitudes which one performs to extract the low energy effective field theory limit of string theory, but it's non-perturbative in alpha prime. It's harmonic and it's not a constant effect. The typical time scale can be within the ballpark of.
Massimo, can you finish very soon, please?
Yes, I will. So let me give. Yeah, this is the ballpark. So, for instance, for frequency which are in the range of A LIGO or Virgo, one can play with numbers, and for inverse tensions which are in the gut scale and the mass of the object which is around the mass of the black hole, one get visible, detectable. So let me wrap up. So gravitational wave observation may discriminate black holes from fastball, in particular measuring multiple moments like M2, S3, or S2. One can distinguish one from the other. Clearly, one need a more reliable distribution of microstates, for instance, for non-SUSY black holes, or explicit solution for microstates for non-supersymmetric black holes. As we know, quasi-normal modes dominate the ring-down phase of mergers of black holes, and decay time can be very different for and longer for fastball than black holes. There are other effects like echoes, and maybe new tools. I skipped this topic, but if you want, we can talk about it. Quantum cyber-Whittaker can help understanding the structure of this quasi-normal mode. There are other string correction to the gravitational wave profile, which can also give rise to new quasi-normal modes because of the fact that the string resonances are unstable, and so they will be shifted from the real axis. One need to study the correction to the mass and the width of the string resonances if one wants to extract information on the quasi-normal. So let me conclude, and thank you. Sorry for being late.
No problem.
I don't know how much I.
Thanks, Massimo. Shall we just have some brief questions? Daniel, do you want to jump in, or?
Yeah, I did have a question. I mean, I guess my main question is about comparing the multipoles, of fuzzballs to Kerr.
Yeah.
And what would you expect? I mean, except for, of course, if we have a nice collection of microstates of non-BPS black holes, which of course would be wonderful. What could we do to make this comparison more robust? Do you think? I mean, because
as I said, first of all, we expect the distribution of these microstates to be peaked around capital L equals 0. That is where the black hole limit is reached.
Right.
But as far as I know, nobody knows the precise statistical distribution of microstates. So in principle, who knows? The distribution can be a little bit broader than a very sharp peak at L equal to 0. So in a sense, it is still reasonable to consider the possibility that one can have a little bit broader distribution. So the deviation from the real BPS limit of the real black hole limit of the fastball, the microstate, can be relevant. And so clearly this will contribute to these higher multiple moments or multiple moments which are 0 in the Kerr case, and this can be leave an imprint in signals that are collected by gravitational wave experiments or alike.
So I have a quick question, very naive one, but if you're in the scaling regime of microstate geometries...
Sorry, let me turn on the... Yeah.
No problem. If you're in the scaling regime of microstate geometries where you have things that are with big long throats, do these multipole moments and these things that you talk about get washed out by the scaling effect so they just look like black holes or are indistinguishable?
Yeah, sure. But yeah, you are assuming that the scaling regime is the dominant regime in the distribution of these microstates, which I may argue it's not completely well established.
Fair enough. Okay. I would just expect them to look more like black holes, but okay, no, that's fair enough. Samir's got a question though. His hand has been up, so I should let him.
Yeah, I was just struck by something you said on your first slide, which maybe I didn't understand. So you found the Lyapunov exponent in some cases to be violating the bound which was set on general grounds. What is the significance of that? I mean, is that bound they tried to set then incorrect?
No, what I'm trying to say is that if you take, for instance, an extremal black hole, the temperature of the black hole is equal to 0. So this is obviously violated. I mean, there is a photon sphere also for an extremal black hole, and the Lyapunov exponent, which is determined by the deviation of the geodesics around this photon sphere, does not satisfy the bound set by the temperature of the black hole.
So even for a very small temperature, there would still be some violation.
Yeah. So what I'm trying to say is that at small temperature, when the photon sphere of the black hole coalesces with the horizon of the black hole, the bound is violated.
I understand. I was just trying to understand. So what does that mean? That means that the proof that Maltner, Shankar, Stanford had is wrong, or that this situation doesn't?
No, it's not wrong. It's always in physics. The hypothesis is that you have the dynamics is in a sense dominated by the physics at the horizon of the black hole. Now, the Lyapunov exponent, as far as I can tell, is instead determined or dominated by the dynamics at the photon sphere, which is separated by the horizon. Typically, it's close or it's the same order as the horizon, but it's not the horizon itself. By the way, in the other part of the talk, we have shown that even some naked singularity is not so naked in the sense that it may have a photon sphere even if it has no horizon. So to some extent, in philosophy of fastballs, where we want not only to eliminate the singularity of the black hole, but also the horizon of the black hole, what will remain of the black hole is the physics of the black hole, which is the photon sphere. So in fact, when people sell as the black hole horizon, the picture here, this is not the black hole horizon, it's the photon sphere of the black hole. So the photon sphere is there, and we expect fastballs, exotic compact objects, gravastar, whatever has a microstructure at the horizon, to keep the photon sphere, even if the horizon could be washed out by this microstructure.
Thank you. That's very interesting. Thank you. Yeah.
Sorry, Guillaume, you had a question.
Yes, I wanted to ask you, Massimo, about the JMART geodesic. So you extract the Lyapunov coefficient, but have you any information about the behavior of the geodesic with respect to the corresponding black hole in terms of the impact parameter?
Yeah.
So how does the geodesic behave?
We studied, I mean, typically the geodesics yeah.
I mean, compared to your draw, for example, for the two charge, do you get something similar for JMART, or it's?
Yeah, sure. We have something. Yeah, so yeah, it's something similar to this. I mean, you have a photon sphere, and in the plane, clearly JMART is easier than other cases because once again, this separation constant is known, and then you can study. Generically, the equation cannot be integrated analytically. They're not written in terms of, but you can study the behavior numerically. Yes.
Mm-hmm. So this picture is qualitatively valid for JMART, you say?
Yeah.
Andre, you had a question.
Yeah, Massimo, can you say again? So you're saying that we will be able to measure the imprint of strings with A LIGO and Lisa? That part was a bit fast. Can you maybe?
Yeah, this is really a toy model. I mean, you can study the scattering of what people call small black holes. I mean, objects that have one in a momentum in a hydraulic string on a tori, 6 torus. And this is really like computing the scattering of gravitons in 10 dimensions. It's not any harder than that. And
but so you would.
Sorry.
For anything to be, I mean, you would have to look at what, near extremal black holes, or?
Well, these are 1/2 BPS black holes.
Sure, but
these are, they carry no angular momentum in 4 dimensions. You can only put excitations in the internal directions. You can actually, at present, we are studying the case in which these objects have also angular momentum in 4 dimensions. It's a little harder, but it's doable. And the important thing is that very similarly to what you do in the gravitational case, where essentially the pole 1/omega, once you Fourier transform, give rise to this memory effect. In the case of the string, there is an infinite number of poles, which are here, which correspond to the string resonances. Now, when you Fourier transform, this gives rise to a series in a variable zeta, which is the exponential of 2i u divided by alpha prime k hat, which is the momentum, the full momentum of the graviton stripped off the frequency, times p, where p is the momentum of one of these objects, which are very massive and compact, if you want. Now, the time scale of this oscillation, this is some complete, very complicated harmonic function. Actually, for some cases, by choosing properly the kinematics, you can even sum the series, and it gives rise to some elliptic function, but this is on the side. So this time scale, delta t, which is here, appears in this denominator. Notice that this is a non-perturbative effect in alpha prime, because it's one exponential of 1/alpha prime. It's like a worldsheet instanton. I mean, you can never deduce it from the low energy expansion of string theory, effective field theory methods. So supergravity, forget about it. But the time scale, if the mass of the object that here is coded in this P3 here, and appears in this combination, if you want, here, is large. So it shouldn't be a string scale object. It should be a very large object. But still, this is completely possible by playing with winding and momentum and the scale of the T6. So if you take the mass to be as large as some solar mass, and you take the string tension to be at the gut scale, you can achieve a frequency for the signal which is 50 Hertz, for instance, very easily. So what I'm trying to say is that a signal of this form can be detected, give rise to correction to the gravitational wave signal that you get in pure generally. Now, if you allow me for 1 second, 1 minute.
Andrew, did you want to follow up though?
Yeah, I wanted to ask, so the calculation comes out of a toy model of having BPS going to non-BPS and then sending out waves. And my question is how, I mean, probably the calculation is undoable if you go away from that simplification, or very hard. But I'm wondering how much it depends on the fact that your calculation uses
No.
BPS
I mean,
states.
by the way, at the beginning we were trying to have 3 BPS, but the 3-point function of 3 BPS is equal to 0 on shell. So we then decided 1 to be non-BPS, but you can put any non-BPS state very easily. Clearly, you know that it's hard to construct vertex operator for higher level string states, which are BRST invariant, unless one relies on the DDF operators. We are also generalized our analysis to the case of coherent states of BPS states, which are not necessarily BPS. And so if you want, I can show you in the paper that already appear in the archive, and we have follow-up papers coming soon.
I see Nick getting a bit nervous, so maybe we do this after.
I think so, because we're about to. I think what we need to do is take a 10-minute break. So let's start the panel in 10 minutes or so, 12 minutes and at 10 past 5, and then but let's wrap it up now and say thanks again, Massimo, and we will.
Okay, I will be there during the discussion. So if you want, ask
absolutely. So get appropriate for the follow-on conversation. Let's kill the recording now, Joseph.